lecture, we ended on looking at the action for the Yang-Mills times Yang-Mills double copy. And as I said, matching that to the actual amplitudes is difficult, but it was done a long time ago in the context of string theory, so it's really coming from string theory. But I figure I should point out a few things which I forgot to mention yesterday. So as I said, this action is basically the Einstein-Hilbert one plus some matter, and the matter is a dilaton and a two-form or an antisymmetric tensor. But one thing to note here is that the matter kind of appears quadratically. Here is obvious that it's a quadratic term for the matter. Here, okay, the H, which involves the B field, is quadratic, and then there's some nonlinear part here. But the fact that it appears quadratically means that this B field has to be pair produced. It cannot be sourced by the other fields. It has to always be pair produced. And that means that when we compute amplitudes at tree level, we can just forbid this B field to be on the external states, and then it will never appear inside the tree level amplitudes, because if it's pair produced, it has to go somewhere onto the external legs. It cannot just sit inside that tree level amplitude. So essentially, this is when you have things appearing quadratically, you can always truncate them away, and this is called consistent truncation. So basically, all tree level amplitudes will be free of this B field. And then when we have done that truncation, then we are here, we can look at the dilaton. So now the dilaton also appears quadratically. So you can essentially also consistently truncate that one. So that means that if you just enforce that you have gravitons on the external lines of your tree level amplitude, you're guaranteed to be only working with Einstein-Hilbert. Right, so basically the conclusion is that tree level, you can consistently truncate. B and phi. All right, another thing that we didn't discuss yesterday is that if you're actually working in 4D, then maybe this Lagrangian is overkill, because it's actually generic for any dimension. So let's think about what we get in 4D. So maybe I just do it over here. So in 4D, in 4 dimensions, we can work with the circular polarization. So we can essentially look at the states that you get there. So you get, first of all, you get the graviton plus helicity, which is this one. Then you get the graviton negative helicity. Then you can get a scalar, which has opposite polarizations. So the two polarizations cancel each other, meaning that it has no helicity weight any longer. That means it's a scalar. And then you, of course, have the other one as well. And essentially, so these are the graviton states. And these are two scalars, which we can always think of as being complex. Essentially, this is a complex scalar. This is complex conjugate. So this we call dilaton, axion. Sometimes people call it axidilaton, I guess, just to put it in one word. And these are scalars. Note that the axion should not be confused with the QCD axion, even though that, well, it does have very similar interactions. That's why it has been given that name, but it's not the QCD axion. Okay, so in 4D, then this action here becomes, you can write it in a slightly simpler way, or maybe more complicated depending on your taste. So the Einstein-Hilbert term is the same. So 1/2 R. And I have set kappa to 1, by the way. That's why there's no kappa or G Newton. Okay, so it's a term that looks like this. Let's see, imaginary part of tau. Okay, so what is tau? So tau here is a scalar, which complex scalar, which people usually parameterize in the following way. So essentially, well, either phi, it would be the dilaton. Sometimes people call e to the phi the dilaton, but obviously the perturbation of the dilaton is phi, and chi here is what people call the axion, I guess. And this imaginary tau just basically picks out this exponential factor and squares it. Okay. Any questions about that? Maybe a bracket. Okay, so these are like two alternatives way, and of course we like 4D, so this maybe is the simpler one to work with in 4D. Okay, any questions? Yeah. So, yep. If it's Kaluza-Klein reduction. I think that's a bit more complicated because then you also get vectors and stuff like that. Yeah, so I think dilaton is used for many things. That's hence the confusion. Of course, when you do a Kaluza-Klein, you also get a dilaton, but it's basically used for any kind of. It's usually used for any kind of scalar that appears exponentially in the action. So yeah, it's a very common name, but. Yeah, there is a story related to Kaluza-Klein, but I don't think you can obtain this precise action from Kaluza-Klein. At least not without doing additional truncation. Okay, good. Yeah, and I should also point out that these actions are maybe not very useful, but because if you want to compute an amplitude, you would just do it using double copy. But it's good to know what you're actually computing. So there it is. Okay, so the next thing I'm going to talk about today, and this is only going to be a brief discussion, and I will maybe come back to it later, is loop level generalization of Color-Kinematics Duality and double copy. So let's talk about loop level. Generalization. So let's start with our color-dressed gauge theory amplitude, which I use this curly script for. And let's indicate that we're now going to work at loop order L. And likewise for our curly M, which I guess is our gravitational amplitude, we're going to work at also loop order L. So now we're typically going to have some integral. Well, maybe I should write it the other way around. We typically have a sum, again, over cubic graphs. So I is just some cubic graphs. Well, let's just say I cubic. And then we have an integral. So basically for each graph, you're going to have some loop integration. So let's just do it very schematically. If you're in D dimension and at L loops, you're going to have a D times L dimensional loop integral. And if you get your factors of 2 pi right, you might also put dl downstairs here. That's just convention. And then you have your usual color factor. You have your usual numerator and your usual denominator. So visually, not very much changes. But one important thing that does change is that you might now have to worry about whether you're overcounting contributions. So you might know that certain diagrams you should divide by certain symmetry factors because otherwise you're overcounting. So you need to also divide by the symmetry factor of a given graph. So that's just the standard thing you do for Feynman diagrams. Okay, so this is the symmetry factor. It turns out that at tree level, you can always define your graph such that there is no symmetry factor, but at loop level, you cannot do that. Okay, and then double copy is basically the same, and I guess I'm running out of space, so let me move it down. Double copy is again that all you do is to just swap out. You swap out the color factor for an additional numerator, but other than that, it looks visually the same. Symmetry factor is the same as in the gauge theory case, but now you have Ni twiddle, Ni over the denominator. Well, yeah, this D is the denominator, this D is the dimension, so sorry for the confusing notation. So one important thing here now is that actually the denominator is of course a function of the loop momenta, and that's very easy to work out. It's just, you take your cubic graphs, cubic Feynman graphs, that it will of course depend on the loop momenta. But your numerator will also now be a function of the loop momenta, and it could be quite non-trivial function. Or sorry, each enumerator might be a non-trivial function of the loop momenta. And in order to do this replacement, replacing the color factor with a numerator, you need to make sure that color-kinematics duality is respected. So you need to make sure that there are Jacobi identities satisfied. So, yeah, an important aspect here is that Ni, let's also denote that it depends on L. Let's say Ni or Ni twiddle needs to obey color-kinematics duality. Which means basically all Jacobi identities. Satisfied. And it needs to satisfy it at the level of the integrand. So it needs to satisfy it as a function of the loop momenta. You're not allowed to integrate first and then impose color-kinematics duality. You need to do it before, because this function is sitting under the integration symbol here, and you do the swap. So the swap is basically done before integration. And those of you who knows what kind of complications you encounter for loop diagrams might know that there's no unique way to define integrands. So one has to worry about what does this even mean, that it needs to obey it at the integrand level. But let's say, for clarity, that we can always define an integrand each time we do a unitarity cut. I forget if David talked about unitarity cuts already. Probably not, right? Yeah, but he probably will talk about it today. So yeah, I'll answer your question shortly, but let me just write. So this integrand level, whatever that means, is well defined. For each unitarity cut. Assuming that you cut each loop at least once, which is pretty much what everybody does when they do unitarity method these days. Okay, so the question, yeah? Yes, okay, good, yeah. I didn't say that. Why does it say or rather than and? So this is something I've been sort of not mentioning so far, but it turns out that the double copy actually works if just one of them satisfy color-kinematics duality manifestly, right? So I mean, I was stressing that, you know, in order to replace C with n twiddle, you need to make sure that n twiddle satisfy the same identities as C. But in principle, you know, this n, it doesn't do anything, it just sits there. So it can actually not obey color-kinematics duality. That's actually an option. And of course, by symmetry, you can, you know, it's sufficient that either n or n twiddle satisfies color-kinematics duality. That said, in principle, both of them needs to do it, but you don't need to manifest it, right? Because manifesting color-kinematics duality is hard work, and if you can avoid doing it for one of these n's, then you gain something, right? In particular, I mean, later today we might talk about what kind of theories you can consider, and some theories are easier to work with than other theories if they have a lot of symmetries, if they have, for example, supersymmetry, or if they have some other properties which simplify them. And then it's actually very convenient to pick the numerators that are simple, and you make them obey color-kinematics duality, whereas the numerators which are complicated from the complicated theory, you just say, yes, it should have satisfied color-kinematics duality, but I was too lazy to manifest it, so I just leave it on a non-manifest form. That said, the numerator still has to be, or the amplitude still has to be described by cubic graphs, because otherwise this formalism does not work. So you have to, the minor massaging that you have to do is that you have to make all higher point vertices cubic, which you can always do. It's not very hard. Okay, did I answer the question? Yes. Yes. So this is actually very important because it greatly simplifies calculations, and this also holds true at tree level. I just didn't mention it at tree level. Okay. Any other questions? Yep. The B field. The B field is that? Sorry, can you say a bit louder? Good, yeah, good, yeah. I was a bit confused because I don't see any B field here, but yes. So you're referring to the fact that at tree level, you can do a consistent truncation, which I said over here. And that's, the reason for that is that this B field and the dilaton has to be pair produced. Also the tau has to be pair produced. And of course, at loop level, yes, they can be created and then annihilated, and that's just a loop. That's just a loop of this matter. So this truncation here is hard to do at loop level, and well, I will come back to a way of doing it, but at first, well, approximation, we have to basically say that we cannot get rid of it, so we just keep them. You know, yeah, they're gonna be in the loops, and we cannot avoid it. So, you know, that's how it is. Right? Was there another question? Yep. Say again. You're asking if there's some problems at certain loop orders. Well, in principle, whatever I wrote here works, assuming you can find these color dual numerators, numerators that satisfy color-kinematics duality. So if you can find them, it's straightforward, any loop order, no problem. The problem is, can you find them? And that's known to be a problem, yeah. So there are some cases where we have found the numerators up to 4 loops, but we could not find it at 5 loops. But that could just be that we didn't look hard enough. You know, they might exist, just we didn't find them. And I think for Yang-Mills, there's also some problem already at 2 loops, but again, it's unclear whether this is just, because you didn't look hard enough, or whether, yeah. So there could be problems, but the problem is finding these numerators. I mean, do they exist or not, right? So assuming that they exist, then there's no problem, yeah. Okay, good. All right, so I was going to say a few more bullet points here. What's important here is that you have to be a bit more careful. Like at tree level, you can be a bit sloppy, but at loop level, it's easy to do mistakes. So one mistake that you could do is that you could evaluate your color factors, which you should not do. So color factors CI should not be evaluated explicitly. What do I mean by that? What does it mean to evaluate the color factor? Well, it means to sum over the colors in the loop, right? That's how you evaluate it, and you do some algebra, whatever, reduce them to simpler things. Don't do that. If you do that, you're in trouble. It's basically the same reason why you should not do the loop integration, because you're basically you're preventing this replacement from being done, because the integration will kill certain terms here, which it might not kill here, and the same goes for the color factor. So just to give you a very interesting example, so there's a certain loop diagram, which I usually call the non-planar window. So this is a non-planar window. Well, I guess it's a non-planar. Okay, there's a non-planar window at the lower loop order as well. But let's consider this diagram. So there's no crossing here. And then if I just compute the color factor of this diagram, it turns out to be 0. And that's essentially, I don't know, it's an accident of this graph having a lot of symmetries, and those symmetries are in conflict with each other, and that's why when you evaluate it, you get 0. That doesn't mean that you should actually use that, because I consider that to be like an accidental property. That property does not have to be reflected in the numerator, so let's not use that as an accidental property. Yeah. All right, and another thing that you need to be a bit careful about is that I said here that we're summing over all cubic graphs. So what does that mean? Do we know how many cubic graphs there are? Does anybody have a guess how many cubic graphs there are? Well, one loop, I don't know. No, that's the thing that, that's a very tough question. And it actually depends on how you think about it. In some sense, there's actually an infinite number of graphs, because you can always shift your loop momenta, and you can count that as being different graphs. So essentially what you need to do is that you need to impose something such that you go down to a finite number of graphs. Otherwise tough luck on working with infinite number of graphs. And so what you impose is essentially graph automorphisms. Or sometimes we just call it graph symmetries. You need to impose those on the functions n, ni, and ni triddle. And for example, let me just give you one example. So let's say we're at one loop. So at one loop, we have this ring diagram. So let's call it, what do we want to call it here? 1, 2, 3, 4, whatever, 5. Too many legs. N minus 1, right? So let's say we have this diagram, and then we have to decide where do we say the loop momentum is, right? It's kind of ad hoc where you pick it. Let's pick it to be here. L, this is my loop momenta. But of course, I could have picked it differently. And I could also have, let's draw the diagram. Well, let's draw the diagram again. Well, too many legs again. So 1, 2, 3, 4, 5, n minus 1, n. So I could also pick it to be here between leg 1 and 2, for example. And just to be clear, let me call it L prime, because it's not exactly the same L. But obviously, these two graphs are the same, right? I mean, no sane person would say that these are the different graphs. This is the same graph, so we just say they're equal. So that's one graph automorphism, like a symmetry on the graph. And what does it mean for the numerators? It means that if we have, let's label the numerator slightly different. So let's label it by the external legs. So 1, 2, 3, 4, 5, ... up to n. And then we also write L. So let's take this guy to be that one. And then this guy, we just say, well, let's put equal sign here. So equal to, well, so now, typically what I would like to do is that I would like the first label here to be what comes after L. So that would be 2, 3, 4, 5, and then n and 1, I guess. And then it's a function of L prime. Right, so you need to make sure that these two functions are the same. But okay, what's the relation between L and L prime? Well, L prime, of course, is just equal to L minus P1 by momentum conservation, right? Now you might think this is maybe silly because why would I even introduce two different graphs in the first place? I mean, I could just stick with this graph and never introduce this one. But it turns out that when you do Jacobi's, the Jacobi's generate such graphs, and then you have to decide what to do with them. You have to say, is this a new graph or is it a graph I already had? And with the automorphism, you can map it back to the graph that you already had. Yeah. So this thing that I'm discussing here, that's part of a larger issue that you encounter at loop level. Sometimes people call it the loop momentum labeling problem. It's kind of a trivial version of it. This also features in, I don't know if anybody has followed the surfaceology literature by Nima Hamed and company. It's the same thing there that, Nima is trying to find a global integrand, but it's basically forced to do some winding. He's forced to introduce winding modes, an infinite number of them, and this is all related to the fact that there's an infinite number of ways of labeling the graph. It looks like it's only a finite number, but you can basically shift L by any of the external momenta, and that can be thought of as some kind of winding issue. But I'm not going to talk about surfaceology here, surface hedron or whatever. That was just a minor comment. All right. Yeah. So basically, when you enforce this graph symmetries or graph automorphisms, you always land on a finite number of graphs. You might never have thought about this being important, and that's because Feynman rules by definition respect graph automorphism. Feynman rules respects the symmetries of the graph. So for Feynman rules, this is never an issue, but here we're trying to solve for numerators, and we don't know where they come from. They might not come from Feynman rules, so then you need to enforce this. All right, any questions on that? So then I think I'm going to move on. So I'm not going to talk about loops more today. Maybe in some other lecture I'm going to talk about loops. But yeah. How do you do this without getting confused? Is that what you're asking? Yes. Well, you use some software that is good at dealing with graphs. Like Mathematica is pretty good at dealing with graphs. And it even have functions. I think there's a function called graph isomorphism or whatever, which allows you to compare two different graphs. Automorphism just means that you're comparing the graph with itself. But you can, of course, compare two different graphs and ask if they're the same. So Mathematica does this actually, yeah. If you just implement it, you don't have to think about it, yeah. Okay, any other questions about loops? Yeah. Yeah. Yes, but yes, that's right. Yes, that's a good point. So for planar graphs, you can avoid this issue, and you could, I mean, then you can say, well, is there really a problem at one loop then, because everything is planar at one loop? But you have to remember that, you know, the way I define planar is that it's with respect to a certain ordering. So even at tree level, I talked about non-planar graphs. So here again, if you stick with one ordering, sure it's planar. But if we consider other orderings, then they're like they're you know, you cannot consistently label different orderings, right? So that's a problem already at one loop. And that essentially means is that there is actually no notion of a like a global integrand for gravity, even at one loop. You cannot define a function such that when you apply a gauge transformation on that function, it vanishes. It's essentially impossible. Because if it was possible, well, or let's think of it in another way. Let's think of, like, for each ordering of this ring diagram, let's say I could define a gauge invariant quantity of gravity. That would be very similar to how we do it for gauge theory. But that would basically mean that you have now introduced color orderings into gravity, and you cannot do that, right? So yeah, so no matter how you twist and turn it, you're going to have a problem with labeling already at one loop. All right, any other questions? All right, so as I said, I'm going to not talk about loops any longer. So if you have urgent questions about loops, you should ask now or remain silent. All right, so the next topic I was going to talk about is kinematic algebra. So I mentioned it already, and I figure I should say something about it because it's kind of a mysterious subject. So kinematic Lie algebra. Sometimes we don't say Lie algebra because we want to be ambiguous what we mean. But I think what I'm going to talk about here is a Lie algebra. And if somebody objects, you should let me know. So I said I'm not going to talk about loops, but here's a statement about loops. So if Color-Kinematics duality holds at all loops, and by that I mean that you have a way of finding numerators to all loops that satisfy Color-Kinematics duality, then I would say that a kinematic Lie algebra should exist. Should exist. I don't have a proof of that statement, but it feels very intuitive to me that that has to be true. So if somebody disagrees, you should maybe write the paper. But anyhow, so let's think about what is, well, first of all, let's compare a color Lie algebra with a kinematic Lie algebra. And maybe over here we put kinematic. So obviously the most important thing in a color Lie algebra is the generator and the structure constant, right? Forget about this tilde that I introduced in 2 lectures ago. It doesn't matter here. And so, yeah, so basically the generators and structure constants. I mean, there could be other elements in the layout. Well, there could be other objects that you can produce from these guys, but let's not talk about those. And for kinematic algebra, we want something similar, right? We want something that's similar to T and something similar to F. So let's give them a name. So let's call this one L mu. And let's call this thing here V mu nu rho. And well, I put an index here because I know that I need something to match this index. So let's put an index there. Might as well put a Lorentz index. Why not? And then I need 3 indices here, which needs to be the same. So let's put 3 Lorentz indices there. And yes, the way to think of this is that this, and I should say that there might be other ones, but let's just stick to the ones which says something about vectors, vector representation. So this one here, actually, we should think of as being a differential operator. I will come back to that. Differential operator. Just like the T's are operators. Well, we usually think of them as matrices, but matrices are basically operators, right? And this guy here, here we just think of that as being a number. I guess this is a matrix, this is a number. So this thing here should be something which is not an operator, but this is actually a Feynman vertex. That's why I call it V. And I should also say pictorially, let's give a picture as well. Of course, you know that I used these pictures already for color graphs. I forget if I put wiggles or not. I probably didn't put wiggles before, but let's put wiggles because it's in that joint. And okay, I kind of run out of space here. For this generator here, we can just think of it as being something like this, right? So yeah. So this again, this is not. So this is a Feynman vertex. This is not quite a Feynman vertex in color space because there's some free indices here which we're kind of ignoring. And the same thing goes here, right? That here we should also think of this as being like mu nu rho, and then we should think of this thing as being this guy. But again, this is a Feynman vertex. This is not, because this has some operator properties. Okay, so far everything was very abstract. One more thing that I need to point out before I get a bit more explicit. Well, we need to ask how many generators do we have? Because right now it looks like we don't have very many. So here, of course, we have like NC, like if you're doing SUNC, then we have NC of these guys. How many do we have here? Well, it looks like we have 4 if we're in 4 dimensions, because mu runs from 0 to whatever 3. But that's a misconception. We need to think about, in kinematic space, we also have momenta, right? So there's also momenta here. This particle has a momenta p. Here you have 3 momenta: p1, p2, p3. So in fact, this L is a function of the momenta, and this guy is a function of p1, p2, and p3. And of course, by momentum conservation, we can typically eliminate one of them. So it's important here that this is only a function of p, and not whatever this thing is, which haven't specified what that thing is. It only has one momentum. Okay, so this means now that we can get an estimate how many generators there are. There's infinitely many, right? Because for every p, there's going to be a generator. In fact, it's even worse. It's uncountably many generators. because P can take any value, any real, well, P, any real, any real number in Minkowski space. So infinitely many. Okay. Yes. So let's give an example. I mean, maybe right now maybe it sounds like I'm making things up. So let's give a concrete example. And here I'm just trying to answer the question: do we know any such kinematic Lie algebra? Yes. One famous example is actually diffeomorphisms. So it turns out that the generator for diffeomorphism can be written in the following way. So basically, it's a plane wave factor, and then it's just a derivative. Usually, that's not how you write diffeomorphism. Usually, you just write just the derivative itself, or the derivative times any function, which is dotted in. But here, I want to work in a certain function space, which is plane wave basis, right? So that's the generator. And you might wonder what is X doing here? Well, I mean, there's an operator. It needs to act on something, so it needs to act on X, right? So one way to think of this diagram here is that you have the operator on one side and you have X on the other side. Okay. Now I lost track of where I am. Okay, so I should say you might be confused exactly what diffeomorphisms are doing here, but just think of it in an abstract sense that we have some function x, and of course you can do some transformation on this function, to a new coordinate system, and that will be like a diffeomorphism, right? So just think of it this thing acts on functions. Never mind what these functions mean. Yep. This is just math, no physics. Just think of you have a function, and I want to do diffeomorphism on that function's coordinate change. That's the generator. Of course, to do a finite transformation, you have to exponentiate the generator and so on. And I wasn't planning on talking about that. But we can compute the commutation of two such generators. And I think I'm actually going to leave it as an exercise. It shouldn't be very hard, but maybe I'll leave it for you guys to do it. But the point is that it should be a standard Lie algebra. So you should have your structure constant here. Let's put one index up. That seems convenient. P1 plus P2. I think you can get a bit more fancy by writing it as an integral. Let's see. Sorry, I lost track of where I am. Okay, V mu nu rho L rho minus P3, and then a delta D P1 plus P2 plus P3. That should be the same as this thing, modulo some factors of pi, which I dropped. Sometimes people put this, I don't know, do something like that to denote that I have removed the pi's. Anyhow, so what I'm going to do here is I'm going to leave it as a homework. Compute V mu rho. It's not very hard. And so if things have been perfect here, this V would have been the Feynman rule for Yang-Mills. It turns out it's not the Feynman rule for Yang-Mills. but it's 1/3 of the Feynman rule of Yang-Mills. So I let you compute which third it is. So yeah, so that's a problem here, and that's sort of what I kind of indicated with putting 2 indices down and 1 up, is that this vertex is lacking permutation symmetry. It obviously has an antisymmetry in mu nu, which is good because we actually know that the kinematic vertex should be totally antisymmetric. So it has the right antisymmetry property in these 2 indices. But in this index, it has no symmetry property actually. So it does not give Yang-Mills. In fact, it doesn't give any kind of Lagrangian whatsoever, because it doesn't have the properties of a Lagrangian. The Lagrangian should have permutation symmetry when you work out the Feynman rules. Yeah, so problem here, V mu nu rho, which depends on P1 and P2, not totally antisymmetric. And that's why this is not the kinematic algebra of Yang-Mills, but it's more a kinematic algebra of a toy model, which is not very realistic, I guess. But it's, as I said, it does give pieces of the Feynman rules, but not the full. Also, it obviously does not give contact terms. Yang-Mills has contact terms. This is not giving that. So not from so V mu nu rho, not from a Lagrangian. Or theory. All right. Or maybe let's say QFT. Okay, so let's try to find an actual kinematic algebra that works for our purpose. So this is example 1, and then let's do example 2. Okay, so we talked about diffeomorphism here. Now let's talk about something closely related. So volume preserving diffeos. And we're going to do it in 3 dimensions, because that's where things are nice. I don't know if you know about what volume preserving diffeos are, but essentially what they are is that when you change your coordinate, your Jacobian, like in your integral, like if you're doing an integral, you compute a Jacobian factor. That Jacobian factor should be 1, such that the volume is not changing. And in terms of the generator, it actually implies this constraint. And there's a good reason why I put the index upstairs now, but I'll explain shortly. So that's the constraint, and you might recognize that constraint. That's Lorentz gauge. So volume preserving diffeos are generators in Lorentz gauge. Lorentz gauge. Okay. Okay, so let's try to find an explicit formula for these generators. So obviously it has to be closely related to what we wrote there, but we have to solve this constraint. And it turns out that that's actually quite simple to solve in 3 dimensions. So L mu of P is equal to the Levi-Civita in 3 dimensions, mu nu rho, P rho, e to the I p dot x d nu. Okay, so now you can see if I hit it with a derivative, I'm going to get another factor p downstairs, and that's going to kill the Levi-Civita, right? Because the Levi-Civita is antisymmetric. So we can essentially write that as a projector. Let's call this projector delta. So this is, by definition, a projector applied to my regular diffeomorphism generators, which I had over there. So this is the definition. You can work out yourself what it is. It's this term, this term. Yeah, that's it. Okay. Okay, so now we compute the commutator of two generators. And let me do it for you. So we're going to get this delta factor again, so of P1, so mu prime, delta factor of P2, nu prime, and then epsilon mu nu rho prime L rho P1 plus P2. Okay. You can check this if you agree. Check that you agree with this. Yeah. So now the claim is that this should essentially be our Feynman vertex. This should essentially be our vertex mu nu rho, which is a function of P1 and P2. However, it kind of looks again a bit asymmetric. Like it looks like mu and nu and rho are different. Two of them upstairs, one of them is downstairs. So it looks again a bit asymmetric. But in this case, actually, it turns out to be fine, because we can actually interpret what we have done here. So we can interpret this guy here as being the actual Feynman vertex, and then we can just interpret this as being Lorentz gauge projectors that came from somewhere. And the word it came from was actually from the propagator, and then you can interpret this as like an amputated diagram. So if we say that our propagator, whatever g of p, is equal to delta, I guess it's two indices, mu nu of p over p squared. Let's say that that's our propagator, and we say that our vertex mu nu rho is equal to epsilon mu nu rho. Then we're actually in business, and you might recognize this propagator and vertex. This is the propagator and vertex of Chern-Simons theory in 3 dimensions. And also the reason why we only had this projector on 2 of the guys is that because we're basically doing some kind of similar, we're doing some kind of recursive construction. So as you're doing more and more commutators, you will get more and more of these deltas, but you don't want to double up on the delta. So that's why you need one index which do not have this projector, because otherwise you would overcount. So you can think of that as very similar to how you do things when you, for example, solve recursively Bern-Schiele. I don't know if you know what Bern-Schiele recursion is, but it's kind of like this, that you have one leg which is special, or if you when you solve equation of motion, there's one particle which is special, which is your field, and then the other ones are your external particles, I guess. Anyhow, any questions on what I just did here? Yeah. Yeah. Well, it's not a metric because it's antisymmetric, and usually you want metrics to be symmetric. But you can square it. You square it, and then it becomes symmetric. So we can do that exercise. So mu nu p, and then I guess I do delta nu rho of p, right? So that becomes that becomes p squared eta mu nu, well, whatever. Let's do delta. Delta mu rho minus p mu p nu rho. Sorry, right. All right. So that you might recognize. That is the norm. That's the normal projector that takes you to Lorentz gauge, right? So yeah, you can think of that as the metric that stays within Lorentz gauge or whatever, or what's the right word? It's the identity element of the subspace for fields that obey Lorentz gauge. Yeah, so it's a metric, yeah. But I guess, so this delta is more like a square root of a metric, I guess. Yeah. All right. Any other questions? Yeah. Yeah, that's right. So in Lorentz gauge and for Chern-Simons theory, it works. So there is, so there is a kinematic algebra for that theory in that gauge. Yeah. And that actually took us a very long time to figure out. I mean, I think it took us more than 15 years, maybe. And that's because we're not thinking of Chern-Simons theory. Well, there was some early work on Chern-Simons theory, but this was Chern-Simons matter theory. You might have heard of ABGM theory and so on, which is a completely different context of Chern-Simons theory. And so we didn't think about this, but it turns out that, yeah, this one just works straightforwardly out of the box. Let me say maybe a few more things about Chern-Simons theory, because otherwise there might be some confusion. So you might know that it's topological. So what exactly are we computing, right? Certainly not amplitudes. Let's just say Chern-Simons. So the Lagrangian is basically just a trace of, people usually use this form notation. So it's a form, A is a one form gauge field, and then this is the interaction term. Yeah, this wedge product here just means that you're contracting with Levi-Civita. That's what it means. Here you're also contracting with Levi-Civita. And there's also a coupling. There's a coupling K, which is integer, but it doesn't really matter for our purposes. Okay, good. So that's the action. And I should have pointed out that that's the action before you gauge fix, but then you also need to add, after gauge fixing, you need to add Faddeev-Popov ghost. And I'm not sure if I'm going to spell this correct. Ghosts. If you want to do loops, you have to do Faddeev-Popov ghost just the usual way. It's actually exactly the same Faddeev-Popov ghost as in Young-Mills. And I should say that if you include those ghosts, it also works. There's a kinematic algebra that includes the Faddeev-Popov ghost as well. But what's important here is that the equation of motion here is just that the field strength is equal to 0. Well, I can put the indices here, but field strength is a form as well. So this equation of motion is that field strength is 0, which has the solution, of course, that A mu of x is equal to p mu e I p dot x. So there are solutions corresponding to plane waves in Chern-Simons theory, but you might recognize what the problem is. That's a gauge transformation, right? So you can scatter things in Chern-Simons theory, but you're scattering pure gauge. That's pure gauge. And that means that since you're scattering pure gauge, you're going to get 0. So the amplitude is 0. And that's because it's topological theory. However, yeah, so that means that we cannot check what we're doing here by computing an amplitude, but we can check it by computing things which are not amplitudes. For example, off-shell correlation functions. So off-shell functions. So they are not equal to 0. But of course, they are, they're not physical. Off-shell correlation functions in a gauge theory are not physical for the fundamental fields, so they're not physical. As soon as you make them physical, you get 0. But before that, they're non-zero, and they're non-trivial objects. And you can also use them if you want to compute observables in a Chern-Simons theory. You can also use that for Wilson lines. But here I'm talking about the context where I'm not considering the Wilson lines. Okay. All right, so that's an example where everything works beautifully. It works to all loop orders. And the statement I made here is correct for this case, that there is color-kinematics duality to all loops, and there is a kinematic Lie algebra as well. Let's talk about another case which also works to all loops, which usually we don't talk too much about because it's trivial. So this is the bi-adjoint scalar. Sometimes people abbreviate it as BAS. Sometimes people also call it phi cube theory because it's basically phi cube theory. Before I think about the Lagrangian, let's just think about the amplitude of this theory. Essentially, it's going to answer the following question: What is this object that we introduced in yesterday's lecture, this propagator matrix? Well, the answer to that question is that that's an amplitude, which we can color dress. This is a color stripped amplitude, so we can color dress it by putting in its color factors. I'm running out of chalk. There we go. All right, so remember the formulas from yesterday. We had this matrix, then we can multiply it by color factor. Now I introduced a second color factor. And if we just do all the logic we did yesterday, but in reverse, we know that this actually should be a sum over all cubic graphs. Ci twiddle over di. And you might know that if your Feynman diagrams just looks like 1 over the momentum invariance, it's probably a scalar theory, and it's probably phi cube theory. So this is a phi cube interaction. And furthermore, I can write down the Lagrangian. So the Lagrangian is, sorry. So it has two adjoint indices. So typically we use the little a and capital A to denote those two adjoint indices. So they're different adjoint groups. And I guess also let me introduce, well, there's a lambda there, that's my coupling, I guess. It has two structure constants. And this tilde is different from the tilde I had in previous lectures. Okay, so every field has two adjoint indices belonging to different gauge groups that don't have anything to do with each other. And so you address the interaction with two structure constants belonging to two different gauge groups. or groups, whatever. In this case, they're not gauge groups, they're just some flavor groups, I guess. And you can say that this one trivially satisfies color-kinematics duality because now I have I'm basically calling this the color factor and this the numerator, but they're actually both color factors. And they're just going to satisfy all the Jacobi identities given that this C comes from a Lie algebra. And so everything is just going to work to any loop order. That said, this theory is of course not very physical. I don't know what they could possibly describe. Chern-Simons theory described many interesting things, but I have no idea what this theory is actually describing. What's the physics? But it is an example where things work trivially. So therefore, it's a very interesting case study. Like if you want to understand what does the kinematic algebra kind of mean, well, it has to mean exactly what it meant in this case, because this case is the trivial case. And it also gives a very nice interpretation of this partial amplitudes. And this was actually found in the context, of CHY. I don't know if you heard of CHY, Kachasohe and Yuan. They're the one that noticed that this matrix here is actually the inverse of the KLT matrix, which I guess it's kind of trivial in hindsight, but it wasn't noticed before that. Yep. Yeah, I mean, this is trivial, so this just works. Works for anything, any loop order. That said, I'm not sure if the loop, what does the loop correction in this theory mean? I mean, are they even sensible? Usually, phi-cube interactions are not very happy. Yep. Well, in this case, since it's just two color factors, you basically just have two copies of generators, two copies of F. Yeah, so it's. Yeah, well, I mean, you can think. Yeah, I mean, you can always promote this to a differential operator, but it's kind of a trivial one. It's a matrix, I guess. Yeah, so it's not a proper differential operator. Yeah, unless you take some limit, maybe where you have infinite number of, like if you take S to n and take n to infinity, I suppose you get some. I think there's some well-known things that happen when you take n to infinity. I think you get some Virasoro algebra or something like that. I don't know. Say again? So, what? W. Okay, yeah. He's the expert on W algebras. Yeah. Yeah. Yeah, I mean, every theory needs to have its own algebra, I suppose, right? I mean, assuming it exists. I don't know if it actually exists, but if there is a kinematic algebra for Yang-Mills, then that kinematic algebra is going to be different than for other theories. I mean, in the trivial case where you just add matter, that just means that you need to add more generators, I suppose, right? So, there's many interesting theories. There's like higher derivative gauge theories. Their kinematic algebra is presumably quite different from Yang-Mills, if it exists. I don't know if it exists. Yeah. No, I mean, as I just gave you an example, like diffeomorphisms is not a theory, but it is a kinematic algebra, right? Yeah. I think in some sense, diffeomorphism is the the vanilla example of a kinematic algebra. I guess you could also do, as I said, you can do volume preserving diffeomorphisms. That's another kinematic algebra, and then you can do symplectomorphisms. That's also a kinematic algebra. Yeah. Yeah. That's an interesting question. I don't know. I don't know. I mean, it's not going to be a GR. So then you have to ask yourself: is there some room? Is there some wiggling room for some other theory that has been two particles? And I mean, the answer is usually no. but maybe there's some bizarre version. Maybe there's like an unphysical version of GR. For example, sometimes people talk about self-dual Yang-Mills. Which I guess I should have mentioned because that also has a kinematic algebra. But that's of course an unphysical version of Yang-Mills. It doesn't respect CPT. And there's also self-dual gravity, which is an example of a gravity which is not GR, but it has all the properties of GR. But again, it's unphysical because it does not respect CPT. So it could be that, yeah, maybe if you take two copies of this kinematic algebra for diffeomorphisms, maybe you get some unphysical version of GR, which is interesting. Maybe it's interesting for some reason, yeah. I can't hear. Very good question. Yeah, I think it hasn't been figured out yet exactly what it is. I mean, we wrote down a Lagrangian, but that's a gauge-fixed Lagrangian. And the question is, how do you do the ungauge fixing to match something that's already known in literature? So there has been some papers that says that it's Kodaira-Spencer gravity. I don't know if you know what Kodaira-Spencer gravity is. But I think that statement is maybe not exactly correct, because Kodaira-Spencer gravity lives in 6 dimensions, and Chern-Simons lives in 3 dimensions, so it's more like some compactified version of Kodaira-Spencer, and so maybe that should not have the name Kodaira-Spencer, I don't know. Yeah, if you know anything about string field theory, you might also know that you can get Chern-Simons theory from string field theory, and that's just the open string version, and that's the closed string version, which is Kodaira-Spencer. So that's a deep connection there to string theory, I guess. Okay, how am I doing with time? Am I doing really bad? Okay, yes. Yes, I think I probably want to end slightly early today, so we have time for lunch. But yeah, let's talk about matter. So far, I pretty much stayed away from matter. Well, I gave you some scalars, but you could say that that was just like pure scalar theory, like the Biot theory. Oh, sorry. Even before I get to matter, let me give you one more example of a theory that works relatively well. So that is, where did I do it? Here. So let's put it over here. So it's the nonlinear sigma model. Nonlinear sigma model. So the Lagrangian, there's many ways to write the Lagrangian, but I think one standard way is writing it like this: trace of d mu u, d mu u, and there's a dagger here. So U here is a unitary matrix, unitary matrix field, I guess, which you can always parameterize as e to the I phi, where phi is Hermitian scalar, I guess. And so this dagger here is basically the inverse. Well, dagger means, well, yeah, I guess you have, well, I think it's correct that way I wrote it. And there's also some coupling. I think people usually write it using an F. This has a coupling, and there's a coupling here as well. So the claim is that this theory also appears to satisfy Color-Kinematics Duality, and that's kind of quite non-trivial at first sight, but there is some connection between this theory and Yang-Mills. So maybe in hindsight it maybe is less surprising. But the point is that people have, obviously this Lagrangian does not look anything like what we would expect from Color-Kinematics Duality, but there is a way to massage it, and so there's been some work due to Clifford Chang and Xiao Shen. So there's a Lagrangian known that manifests Color-Kinematics Duality, up to one loop. So all 3-level and all one loop graphs. Not beyond that though, right? So kinematic algebra up to one loop exist. Doesn't mean that it doesn't work at higher loops, just nobody has done it. Also, this way of the way that Zhang and Shen realized it is that they introduced 2 fields, and so it's a bit asymmetric, and not sure if that's going to generalize to higher loops, but there is some version of a kinematic algebra that seems to work very nice in this theory. Okay, good. Unless there's any question about that, let's talk about matter. So matter, the way I'm thinking about matter here is that now we're putting something in the fundamental, like fundamental quarks. And when you include matter, this gives a lot of new theories that you can play games with. So in some sense, this gives what people call web of double copy theories. Well, there's some theories which you could also say have no matter, but whatever. It's when you include matter that it goes kind of haywire. So, for example, let's consider the most important case, because it's the name of the school, so QCD. So let's consider QCD. So we just add a bunch of quarks. Let's call the quarks Q. And then we have the Dirac Lagrangian here. So each quark could have a different mass, so let's include a mass. And I guess there's a sum over Q, I guess, if you have many quarks. I'm a bit schematic there. Well, maybe I should put an index somewhere. What index should I use? I don't know. F, I guess. Flavor. So basically, this theory will have some SU NC times SU NF symmetry. So a local gauge symmetry and a global flavor symmetry. And I'm not gonna work out any details here because it gets a bit messy. But the claim is that Color-Kinematics Duality seems to work. And double copy. Works. At least at 3 level. Well, let's say it seems to work. Seem to work. And the reason I'm being so sketchy here is because there's no, as far as I know, there's no proof of the statement that it works at 3 level even. So we checked that it works up to 8 points at 3 level. And then there's been some loop level calculations as well, but typically very, very simple ones. So there's lots of things to prove here. But just now, I mean, take my word for it now, and if you disagree, write a paper. But okay, so the interesting question is not whether it works, but the question is, what is the double copy, right? So what is the double copy? Seems very relevant, right? Because this conference is called QCD, meets gravity. So which gravity does it meet, right? Okay, so again, we can just analyze it at the level of asymptotic states. So first of all, just begin with the usual one, which is just a vector times vector. And we know that that's going to give us a graviton, it's going to give us a B field, and it's going to give us a dilaton. And again, I'm working in D dimensions here, but you can also rephrase it in 4-dimensional notation. But then the interesting part is now what you get when you double copy a quark. Let's say with an antiquark. I think that's the more interesting. Well, that seems to be the right way to doing it. So I didn't say here, but the quarks, of course, are in the fundamental. That's why there's no trace here. It's just this is the antifundamental and this is the fundamental. And here, whether things is whether things in the fundamental or antifundamental, of course, doesn't really matter because you're going to strip off the color. But let's just write it like this for looks nice, I guess. So this here, you can kind of now just tensor, like just think about the little group of quarks, and you think about what you get if you tensor spin 1/2 fermions. Well, obviously they're spin 1/2, so whatever you should get should be spin 1, right? Spin 1, so a vector. But you can also get a scalar. Let's call it curly phi. And you can figure out how many there are as well. So let's assume that we have, I guess typically you have, well, it's a little bit ambiguous, but let's say that we have 2 states here and 2 states here. Usually we say that the quark has 4 states, but let's just think of it as the particles and antiparticles or whatever, so something like that. Then you should expect 4 states on the right-hand side. And so this guy is a vector. So in 4 dimensions, this is a massive vector because the quarks are massive. So this actually has three states in 4 dimensions. And this is 1. So it seems to work out, right? 2 times 2 is equal to 3 plus 1. Good. And you can think about what happens if you're in higher dimensions, then probably it's more complicated. Okay, so this is a Procca field because it's a massive vector. It's not a photon because there's no, well, I guess a Procca is a photon. It's a massive photon, I guess, but yeah. Yeah, okay, good. So let's see how am I doing with time. Okay, so let me just make 2 observations here. Why is this interesting? It looks like, right now it looks like garbage, right? I mean, it looks like, why would I be interested in B, phi, V, phi? I mean, that's just a lot of garbage. But it's actually, there's one very interesting case. So set the quark mass to 0. You can always take that limit. That's an interesting limit. Then let's work in 4 dimensions, which is the real world. And lastly, this is going to be a bit weird. Let's set the number of flavors to be -1. So we have -1 quark flavors. Okay, so why is that interesting? It's because now what we have done is we actually have turned these fields into ghosts, right? Because this minus sign is basically going to have the effect that each time you have a closed loop, you're going to get a minus sign. That's basically because each closed loop has a factor of NF, and we put in a minus sign. So they are basically ghosts now. And in fact, what's going to happen if you do it the right way, maybe I skipped some steps here, but it's going to cancel. It's going to cancel phi and chi in 4 dimensions. So it's going to cancel the dilaton and the axion in loops, similar to how Faddeev-Popov ghosts work. You might say, well, this scalar cancels that scalar, but what's canceling here? Well, you have to now take the massless limit. Then there's a scalar is gonna pop out here, and you're also gonna get the scalar from this guy. So that's gonna be a cancellation between these two guys. And also, what I should say that now it's very important that you pick your fermion wave function to be the plus helicity times the minus helicity, because then you're going to get the scalar, and it's the scalar that you want to cancel. And these lambdas are just the same lambdas as David has been talking about, the on-shell polarizations. I guess usually we put a tilde there, right? Or maybe it's the other way around. I think it's the other way around. Okay, good. And maybe I should end there. Yeah, I think I should end there.
Okay, guys, so we have time for one quick question, an urgent.
Does anything happen, anything interesting happen in the n going to infinity limit?
NF, you mean? The number of flavors to infinity?
Yeah.
I don't know.
No, could be the gauge one. So,
well, I mean, as I remarked before, if you take SUN to and n to infinity, you get some W algebra, and you should ask that guy. I don't know anything about W algebra. Yes, it's a well-known thing. Yeah, I think that's the only interesting thing that I know. Yeah.
Okay, guys, so let's postpone now the questions to discussion section so we'll not get too late to the colloquium and to the lunch. So let's thank Henrik again. We will be back at 2 p.m. because of the colloquium, right? Don't forget about that. And he is the one who's giving the colloquium, so don't forget about it.